Namaskar and a very good afternoon to all of you who are joining to this, the 37th PRL Ka Amrut Vyakhyaan. On behalf of PRL, I, D. Pallam Raju, welcome all of you who are joining us live in today's event via WebEx platform and PRL's YouTube channel. PRL came into existence in the year 1947, and so, along with the nation's 75th year celebration of Azadi Ka Amrut Mahotsav, PRL is celebrating its Platinum Jubilee year. As part of this Platinum Jubilee celebrations, PRL has initiated several exciting programs and events, and one of them is this lecture series, which is called PRL Ka Amrut Vyakhyaan, wherein we invite people of eminence in the fields of science, engineering, technology, arts, literature, business, and law to share with us their excitements in their respective domains so that we can enhance our knowledge. There will be 75 of such Vyakhyans or lectures in this series, which started way back in 4th August last year and will be going on until the early next year. All the lectures delivered so far are available on PRL's YouTube channel, and I encourage all of you to view these excellent lectures. I also take this opportunity to request all of you to please stay tuned on all Wednesdays for the forthcoming lectures as well. Today, indeed, we are delighted that the 37th PRL Amrut Vyakhyaan will be delivered by Professor Lisa Kewley. She is from Australian National University. So, and she'll be talking on the topic of Astro 3D. On behalf of PRL, I would like to thank Professor Kewley for kindly accepting our invitation and agreeing to deliver this Vyakhyaan. To formally introduce Professor Lisa to the audience, I will invite my colleague, Dr. Manas Samal. Over to you, Manas.
Thank you, Professor Pallam Raju. Good afternoon, everyone. Friends, today, it is an honor and privilege for me to introduce you today's speaker, Professor Lisa Jennifer Kewley. And Professor Lisa Jennifer Kewley is a professor and Australian Research Council Laureate Fellow at the Australian National University. Professor Kewley obtained her PhD in 2002 from the Australian National University. Her thesis was on the connection between star formation and supermassive black hole in galaxies. Then she moved to USA, spent a couple of time. She was a Howard Simpsonian Center for Astrophysics Fellow, and she was also a NASA Hubble Fellow. During these years, she received several awards. Just to name a few, her awards include the 2006 American Astronomical Society Annie Jump Cannon Award, in 2008 American Astronomical Society Newton Lacy Prize Fellow, and she also received US National Academy of Science James Watson Medal. In 2014, Professor Lisa was elected Fellow of the Australian Academy of Science for her fundamental advances in understanding of the history of the universe, particularly star and galaxy formation. In 2015, Professor Lisa was awarded an ARC Laureate Fellowship, which is the Australian's top fellowship to support excellence in research. Professor Lisa is currently implementing her scientific vision through her Australian Research Council Centre of Excellence in All Sky Astrophysics in 3D, shortly called Astro 3D. So basically, Astro 3D combines Australians' radio, optical, ground-based telescopes with international 8 to 10 meter class telescope and as well as worldwide supercomputing facilities to understand the formation and evolution of matter in ionizing radiation and chemical elements in the universe. Today, Professor Lisa will talk about her Astro 3D projects, and she will also briefly talk about the kind of how she is engaged in facilitating the education and outreach program in Australia. With this short introduction, I invite Professor Lisa Kewley to deliver the Vyakhyaan or colloquium to our audience. Over to you, Professor Lisa.
Thank you, Manash. I'm going to share my screen and then go into slideshow mode. Okay, so thank you for that introduction. I'm going to be talking today about Astro 3D, which is an Australian Research Council Centre of Excellence. And this is an overview of my talk today. First, I'll give an introduction into Astro 3D. I'm going to show you some of the discovery highlights in our centre, and then I'll talk about my research within Astro 3D. I'll talk about how Astro 3D is achieving our diversity targets and how we're also helping achieve Australia's diversity targets. And then I'll talk about national benefit, which includes education outreach, as well as some interesting inventions and technology transfer that we're making from astronomy into other areas. So firstly, an introduction into Astro 3D. So Astro 3D is a $40 million research council. It's a centre of excellence. It covers 7 years from 2017 to 2024. So we're just over halfway through the centre, and we have a range of chief investigators and partner investigators, as well as 200 associate investigators and research staff. So overall, the Centre of Excellence is now around 290 people across Australia and internationally. We set up the Centre of Excellence and put together the proposal really to try to take advantage of the next generation of telescopes. We wanted to train the next generation of scientists so that they're ready to lead the discoveries on those telescopes, because astronomy is going to enter a very exciting time in the coming decade and 2 decades, because we're going to make a major leap in size in telescopes. So we're going to go from the 8 to 10 metre diameter telescope mirrors to mirrors that are between 20 to 30 metre size in the optical. And we're going to go from telescopes right now, radio telescopes that are either single dish or cover several kilometres, right up to 1 square kilometre, an entire array that's covering 1 square kilometre, called the Square Kilometre Array. And every time in the past in astronomy that we've made a major leap in telescope size, we've made major discoveries. So, for example, the last time we made a major leap in telescope size, we discovered extrasolar planets around other stars. We discovered dark energy and that the universe was accelerating. And we made discoveries about the black hole within our own Milky Way. And so we expect discoveries on a similar scale with these next generation telescopes. And so we really wanted to use instruments and telescopes that are going to help us to build programs that we can use to make discoveries on these next generation telescopes. And we also had a new opportunity in Australia. The Australian government joined the European Southern Observatory, very large telescopes, which are based in Chile. And there's these enormous instruments on these telescopes, which enable us to obtain optical and infrared images, as well as spectroscopy of very, very distant galaxies. And so we were very, very excited when Australia joined this European Southern Observatory right at the beginning of our Centre of Excellence. And we really felt like kids in a candy store, in that we suddenly had this new opportunity. These are my kids in a candy store. And I really felt just the same when we joined ESO. And so we put together this Centre of Excellence across 14 different institutions. We have 9 universities in Australia. We've got 2 Australian partners. CSIRO run the radio telescopes in Australia. NCI is the national supercomputing facility in Australia. And then we have a range of other international partners based on telescopes and expertise. And now I'm going to talk about the science that we're doing in the centre. So this is just a brief history of the universe. The universe started with the Big Bang, and there was a period of which we call inflation, which is expansion in darkness. And then after about 400 million years, the first stars started forming in the universe, and that really illuminated the universe. And then after a period of time, the first galaxies began forming, and then those galaxies formed and evolved across cosmic time to the types of galaxies that we see around us today. And so our Centre of Excellence is really aimed at understanding the universe right after the Big Bang, when the first stars were forming, right up to the present day, including our Milky Way. We've got 3 goals in the Centre of Excellence. I've I've got a very sensitive mouse, so I apologize if it skips a slide occasionally. The first goal in the center is to understand the origin of the ionized universe. So in the very early universe, in the hydrogen atoms, so the hydrogen was there after the Big Bang. The Big Bang created all of the hydrogen atoms in the universe. And the first stars in the universe ionized the electrons in the hydrogen, and basically the radiation from the first stars ripped the electrons off the atoms, and we call this the Epoch of Reionization. And we're trying to understand what that looked like in the early universe, and this is a 2D map simulation using supercomputers of what it might look like, and we're trying to detect what the universe looked like using the Murchison Widefield Array, which is an array of many of these clusters of antennas in the Western Australian desert. We need 3D though, because when you look at it in 3D using supercomputing simulations, you actually see much more detail. The red here is the hydrogen gas in the early universe, and you might see some little white dots. They're the first stars, and there's circles forming around those stars, and that's the electrons being ripped off the atoms, which makes the universe go from an opaque and hard to see through universe into a transparent universe where we can actually begin to see the stars. And so this is a very detailed simulation based on Australian supercomputers, and we're really using the radio telescopes in Western Australia to try to detect what this might look like. With the Square Kilometre Array in future, we're hoping to be able to map this hydrogen in 3D and to really be able to see this type of structure. We think it's going to kind of look like a sponge or maybe some Swiss cheese. Now with the ionized universe, we actually have we have light in the galaxies, both in the distant universe as well as in the nearby universe, and the electrons are ripped off atoms all the time by stars as well as around supermassive black holes. And so we're using a range of telescopes from the SkyMapper telescope in Coonabarabran, the James Webb Space Telescope, which has just been launched. We're hoping to help discover the first galaxies. And then we're using telescopes in Hawaii and Chile to understand the radiation that's coming from the first stars and the first galaxies, and then how that would change with time. The second goal of the center is to understand how matter accumulated together into galaxies. And these images are from the Hubble Space Telescope. And you can see that galaxies in the very distant universe, 7 to 10 billion years ago is when this light was emitted. So we're looking back in time. And you can see those galaxies were very chunky and clumpy looking. And they're not like the galaxies that we see around us today, which are much more diffuse and more looking like our own Milky Way galaxy. So we all want to understand how matter accumulated into galaxies like our Milky Way over 10 to 12 billion years of cosmic time. One thing we're using to do that is a special technique called gravitational lensing. And this is a technique that was proposed by Einstein. And Einstein predicted that if you have really massive object in the universe, like a galaxy around a massive supermassive black hole or a huge cluster of galaxies, that the gravity around that massive object will be so large that it will bend light. And this is effectively creating a magnifying glass. And we now know that this does happen in the universe, and we can see galaxies where the light has been magnified and bent just like this. And it's effectively creating a telescope that's many galaxies across. And so we're looking at galaxies in the distant universe where the light's been magnified 10 to 30 times through a giant magnifying glass. And that allows us to see galaxies that are much more distant than we would otherwise be able to see. And we can see them in much more detail because it doesn't just magnify the light, it actually expands it on either side. It really is like a magnifying glass. And then we're comparing those galaxies that we see in the distant universe with galaxies that we see in the nearby universe with Australian telescopes. And we're doing this in 3D. In the past, in astronomy, we had 2D images like this of galaxies, or we had a spectrum where we're splitting the light up into its different colors, and each of these lines actually corresponds to an element. So this red line, tall red line here, is from hydrogen. This little red line's from nitrogen. These two lines here are from sulfur. This is from oxygen. This one's from hydrogen, and there's another oxygen line down here. And this allows us to figure out how much oxygen or nitrogen are in galaxies. And it also tells us a lot about the star formation and whether there's supermassive black holes there. But we had single spectra or single images per galaxy. What we really want is to understand how these chemical elements are distributed across galaxies. And to do that, we're using a new technique where we're using imaging spectrographs, which take a spectrum at every pixel in the image. So it's a bit like taking your mobile phone, and for every pixel in your camera on your mobile phone, you get a spectrum, and from that spectrum you can say how much oxygen there is across that galaxy. It's a very powerful technique. And so this allows us to determine the origin of the chemical elements. We know that the chemical elements, aside from the hydrogen and some helium, the elements were made in stars. And these were made in stars all the way across cosmic time, from the first stars right up to the present day. And we're focusing on carbon and nitrogen and oxygen because these are the ones that are easiest to observe in spectra from galaxies. And so we're using observations. We're looking for the oldest stars using the Sky Mapper telescope in Coonabarabran. We're looking for very old stars within our own Milky Way. And this particular star was one that we discovered, and this is the oldest star ever discovered, and it's 13.6 billion years old. We are going to be using the James Webb Space Telescope that's just launched to search for the first galaxies and then to measure the carbon and the nitrogen oxygen in those galaxies. And we're currently using the very large telescopes from ESO in Chile and then combining those with our Anglo Australian Telescope. And so now I'm going to show you some of the discoveries we've made through these programs. So this Sky Mapper telescope in Coonabarabran, it takes images of the sky every night in multiple bands. And then we're finding the most interesting stars. And in particular, we then go and get a spectrum of those stars on the European Southern Observatory Very Large Telescope. And we've discovered the 3 most pristine stars in the universe. And this tells us a lot about the early universe and the chemical elements. And for some of these stars, we can get up to 20 chemical elements. So it's really helping us figure out how pristine the early universe was, and also how pristine stars were in the very early Milky Way, when the Milky Way was just an infant galaxy. We're also doing a program called Galactic Archaeology, where we are trying to reveal the history of our own Milky Way. And what we're doing is we're doing a technique called chemical tagging, where we're taking individual stars in the Milky Way, 1 million stars in the Milky Way, measuring their ages, and then measuring the amount of chemical elements that they've got, carbon, nitrogen, oxygen, up to 30 elements. We know that stars that have the same amount of elements and the same age probably form together, but over time they spread out through the Milky Way and may no longer be together. And so we're trying to use this information from the age and the chemical elements to actually track back the history of the Milky Way. And once we've got 1 million stars, we're about 2/3 of the way there right now through this survey. Once we've got 1 million, we think we will be able to track back the history of our own Milky Way. Now, what we're doing in our centre is we're combining radio telescopes, optical telescopes, and theoretical models. And the reason we're doing this very big project with all these different techniques is that we need to study galaxies in the different phases. Galaxies are made of dark matter, of cold gas, hot gas, and stars. The radio tells us where the cold gas is and about the amount of cold gas. The optical light that you see tells us about the hot gas and the stars. And then theoretical models tell us about the dark matter. And if we really want to understand how galaxies like our Milky Way formed and evolved and how our universe formed and evolved, we actually need massive data sets. We need about 100,000 data cubes of galaxies. And so we're using these Genesis simulations. These are large simulations of galaxy formation and evolution to create the first stars in the universe, and then to evolve those first stars and the first galaxies right up to the present day, and then model our own Milky Way. And what we're doing with these simulations is creating 3D data sets to compare directly with our radio and optical 3D surveys. Okay, so I'm going to show you now some discovery highlights for the centre so far. This is one of my favourites. The Murchison Widefield Array Telescope is aiming to detect the light at the Epoch of Reionization, the hydrogen emission, just when the first stars were forming. And to do that, that's a very, very hard thing to do because there's so much noise in the data. There's noise from our own Milky Way. There's noise from all the galaxies in between us and the early universe. And there's also noise introduced by our own telescopes, and there's noise introduced by things like mobile phone towers and satellites, space satellites. And so Ben McKinley here, one of our investigators at Curtin University, he used the moon to measure the average brightness of the Milky Way at the position of the moon. And this helps us remove the noise from the Milky Way when we're searching for the hydrogen gas in the infant universe. So this is a clever technique, and he's basically looking at the reflection of the Milky Way's light in the moon's light. When we were looking for the Epoch of Reionization, using the Murchison Widefield Array, we improved our ability to detect the Epoch of Reionization by a factor of 10. And this was done by one of our early career researchers, Nicole Barry at the University of Melbourne. We also discovered the most iron-poor star known, and this is a very interesting star. It's got record low amounts of iron, and we think that probably this star was a second-generation star in the universe. It basically only had one star and supernova forming before it. And so this is a record-breaking type of star. And it helps us understand what type of supernova explosions would have happened in the early universe. We used the gravitational lensing technique that was predicted by Einstein to discover the very most distant spiral galaxies. And so here are two observations of spiral galaxies. In these galaxies, the light was emitted about 9 billion years ago. And so we're looking at very infant spiral arms. And these infant spiral arms here, you can see one of them, the other one's probably behind or has dust. And same with this one's sort of on the side. And so this actually is really important. Sorry, my mouse is very, very sensitive. This is very important for predictions of and models of galaxy formation. They really didn't predict that galaxies could form spiral arms that far ago. And so this is a really important discovery. We have a group of Astro 3D fellows who receive prestigious fellowships within our centre. They can choose to work anywhere in any of our partner organisations, and they can choose to work on whatever they would like to work on. Our fellows combined together and decided they would like to work on a joint project and propose for a big survey. And this is a really great program. They combine their expertise. So Caroline Foster was working on nearby galaxies in our what we call a SAMI survey, which I'll talk about later. Trevor was doing more distant galaxies and old evolved galaxies. Claudia's a theorist doing galaxy evolution. Elisabetta is also a theorist where she predicts galaxy spectra. And Emily was doing distant star-forming galaxies, and Chen was doing spiral galaxies. And so they combine their expertise And then they proposed for a very large program on the Very Large Telescope, ESO, on the MUSE instrument, which is the largest optical imaging spectrograph in the world. And they were awarded 200 hours, and they're aiming to look at galaxies in the cosmic Middle Ages when they were basically making a transition from clumpy and chaotic type galaxies into the more diffuse galaxies that we see today. And they're currently collecting data from those telescopes. We achieved a major scientific milestone with our semi-survey. So the semi-survey was aiming to use the Anglo Australian Telescope to obtain data cubes of 3,000 nearby galaxies to really help us understand the nearby universe in terms of how the matter accumulated into the galaxies, how those galaxies are spinning, and then what the chemical elements are looking like in those galaxies. And so this has been completed, and all the data cubes are available to the general public on the website. We also reached the halfway mark of our Galactic Archaeology survey to try to understand and track back the history of our own Milky Way. And the data, the 500,000 stars, has actually now been released to the general public. And another recent discovery is that the Galar team, when they're looking at the Milky Way data, showed that there was a massive flare produced by a supermassive black hole in the center of our galaxies, and the impact was actually felt 200,000 light years away. And you can see that impact on carbon and silicon emission that's very far away from the center of our Milky Way. So this really showed that our Milky Way had a much more dynamic and exciting history than was previously thought. The Galactic Archaeology team also found that there are two outlying groups of stars away from our own Milky Way, and they've got very, very similar amounts of chemical elements to stars in our own Milky Way, and we think that they were originally together, and so that our own Milky Way actually had a past interaction or collision with a dwarf galaxy. Now I'm going to talk a little bit about my own research within Astro 3D. And so my own research right now is really about preparing for the data from the James Webb Space Telescope. So this is a picture of the James Webb Space Telescope being built at NASA Goddard Space Flight Center. It's now been launched. We were tremendously excited and also very nervous when we saw James Webb being launched, and I think all the astronomers were sort of on the edge of their seats, very nervous, because so many things had to come out. The solar shields, which are here shown in silver, had to pop out. The mirrors themselves had to fold out. You had this part of the mirror here has to fold down, and then all the antennas and everything needs to start working, and lots of moving parts. Fortunately, it all operated according to plan, and we're very excited to be receiving data soon this year from the James Webb Space Telescope. And so over the last few years, I've been preparing for the James Webb Space Telescope. And what we're doing is we're developing 3D models of the gas surrounding star clusters, which we call messenger Monte Carlo mappings. This is the first detailed models of the gas for around stars, and we're modeling 30 chemical elements. So we're really trying to understand where the chemical elements are formed in the gas around the young stars. And then what we want to do is to model the gas around the stars in the very early universe and compare it with observations from the James Webb Space Telescope, which is really designed to understand the light coming from the most distant galaxies. Now I'm going to switch gears a little bit and start talking about other aspects of our Centre of Excellence, including achieving our diversity targets. So in Astro 3D, we have a top-down approach to diversity. We decided we wanted to achieve 50% women, which is a really hard thing to do in astrophysics because it's a male-dominated field. So we decided to start by having 50% on our high-level committees. So we have 50% women on our advisory board, 50% on our executive committee. This is our executive management committee. It does all the centre management and planning, hiring, retention, strategic planning, and programs for the centre. So we're setting a role model and really setting the scene for the improvements we want to make. Then we introduced a broad range of diversity initiatives. Our target was 50% women at all levels by 2021. This is just in 4 years. Centre started in 2017. The new initiatives that we introduced include a range of hiring initiatives, such as 50% women on committees, recruitment committees, and on shortlists. We had 50% women leading surveys and projects in the centre, and a wide range of initiatives aimed at improving the culture, developing a positive and supportive culture in the centre, including mentoring circles, climate surveys, codes of conduct, and we have a very detailed diversity inclusion action plan, which you can find here on our website. And actually, we managed to achieve our targets. So this plot here shows you in December 2017, we started with 37% women. We introduced the new initiatives over the first centre. By December 2018, the initiatives were in place. And then we started to see improvements in the number of women in the centre. And this is both in postdocs that we've been recruiting as well as in students. So the amount of postdocs we now have is 56% women, and we've now got 55% women students. Currently in Australian astronomy, the average is at 30% women students. And so we did this through a range of initiatives, as I mentioned, through recruitment. We didn't set targets for recruitment. We didn't say you have to hire a woman, you have to hire a man. We basically just said we're aiming for 50-50. We want 50-50 on the selection committees and 50-50 shortlist, but you hire the best person for the job. And this did work in achieving 50%. And then students select us. We don't select students in Australia. Students get government scholarships, and they can choose who they want to work with and what organisation usually they want to work in. And so we found that once we'd achieved around 40% women in the centre, the amount of female students coming to the centre choosing to work with us increased dramatically, really dramatically. And so I think we reached a tipping point where we'd achieved enough women in the centre and diversity and a positive culture that people wanted to work in our centre. And this is really due to the range of these different initiatives, which I would be happy to talk about in more detail afterwards. Now I'm going to talk a little bit about achieving Australia's diversity targets. So we're also not just aiming at improving diversity within our own centre, but we're aiming at improving diversity in the broader astronomy community. So I wanted to see actually, you know, what initiatives were already being implemented across Australia in astronomy. And so I did a survey of all 17 Australian astronomer institutions. So this is these are either astronomy departments or astronomy and physics departments. If they have an astronomer, I call them an astronomer institution. And so these statistics are 100% complete. And so these initiatives were introduced over the past 7 years. And these are primarily initiated either by centres of excellence, not just our centre of excellence, but there were other centres of excellence doing this as well as the Astronomical Society of Australia introduced an awards program called the Pleiades Awards, which offered universities and institutions prizes, bronze or silver or gold awards for achieving diversity goals. And so these types of initiatives were introduced, including annual climate surveys, a carers fund to support both men and women who need to go to conferences and have childcare either at home or to bring children to conferences and be cared for. Monitoring of colloquium speaker diversity, mentoring specifically of women for promotion, because traditionally women tend to go up for promotion later. Conference codes of conduct, family-friendly meeting hours. So we have meeting hours and colloquia hours only at our universities between 10 a.m. and 2:30 p.m. so that people who are dropping children off at school or picking children up from school can still attend. Lactation rooms, as well as diversity and inclusion policies and committees. And what I found was that most organisations in Australia were actually already doing these initiatives. And so then the question is, were they working? Were they actually doing anything? And the answer is not very much. So across Australian astronomy, this is where we're currently at. And so basically we're at around 30 to 35% women in the student level, and then it goes down to 20% or a bit below 20%. It's about 19% at the level E. This is the full professor level in Australia. The Australian Astronomy Decadal Plan had a target of 33% women here at all levels by 2025. We're not going to achieve that target. And the question is why? Because the universities in Australia did introduce all those initiatives. So I did some research into what's happening at each of these transitions in Australia. So level A to B is from junior postdoc to senior postdoc. B to C is senior postdoc to assistant professor. C to D is assistant to associate professor, and D to E is associate to full professor. And I calculated a thing called the percentage change in the cohort at these positions. So this is the percentage change in men and the percentage change in women relative to their numbers at those levels, to see if there's any difference in how well people are making the transition and promotions at each of those levels. And what I found was that there are these particular levels in Australia where there's stress in the pipeline, and it's at level A to B. Much more women are departing at this transition, departing astronomy entirely than men, and more women are departing astronomy entirely than men at level C to D transition. So this is the assistant to associate professor position. This is very similar to what we're seeing in the US astronomy as well. And so what I did was I generated workforce models, these are published in Nature Astronomy. And these workforce models calculate over time the percentage of women that are going to be in Australian astronomy based on recruitment rates, promotion rates, and departure rates within astronomy. And so what the model showed is that the status quo, if we stick with current recruitment, departure, and promotion rates, because there's so many women leaving at those transitions, we're actually the solid lines here show you the fraction of women at those various levels. We're never going to achieve our decadal plan target of 33%. If we did 50-50 retention, we're still at most levels not going to achieve our decadal plan target of 30%. So it's not actually about retention. What's happening is that the hiring has not been equal. It's been very unequal. And if we did 50-50 hires, where for every man hired, a woman's hired, and this is now being done at many astronomy departments in Australia, if we did that, then we could achieve our decadal plan target of 33% women here, which is around by 2045. If we did 50-50 hires and we're looking at retention and achieving 50-50 retention, then we can actually achieve that target much quicker, by around 2039. And we even achieve close to 50% as well, but there's still a long time frame. If we did affirmative action, and some universities in Australia are doing women-only hires because it's really hard to improve the fraction of women at the highest levels in Australian astronomy. And but we found that when we advertise for a women-only position, we actually get more applicants, and we get high-quality applicants for those positions that we wouldn't otherwise normally get. And so if we did that, then we could achieve our decadal plan target by 2031 and 50% women by 2055. It is going to be a while to achieve 50%, but we're really looking at it, in a long-term basis. So we were able to achieve 50% in our Centre of Excellence, but across Australian astronomy, there's many more women, and there's many more women needed, because it's just such a large pool of people already in Australian astronomy, and most of them at the higher levels are men. And so that was one of the ways that we're helping to impact the rest of Australia. We also have national benefit. And in Australia, to get a centre of excellence, you have to demonstrate that you're going to be providing significant national benefit, and pure science isn't enough. You have to be doing technology transfer outside of astronomy for national benefit. You have to be doing education and outreach, improving the pipeline of girls and people from other underrepresented minority groups into STEM. One thing that we're doing well in astronomy is we're doing skills and expertise transfer outside astronomy. The diversity initiatives making a broader impact is working in astronomy. We're also doing sustainability initiatives, and these also have broader impact on the organizations that we're working in. So I'm going to show you some examples. So we have some really amazing technology in the center. The Murchison Widefield Array is on a very unique radio quiet site, and the Square Kilometre Array phased arrays are using unique focal planes to create 3D data cubes of nearby and distant galaxies. And these are using cutting edge data analysis techniques. We also have these hexa bundles, which are hexagonal fiber optics cables, and they're fused together into bundles. And this is, we pipe the light down these bundles into a spectrograph, and this allows us to obtain a spectrum for every single fiber when we stick that on a galaxy. And what we've developed now is these really clever technique called piezoelectronic robotic positioners. People used to have to plug these fiber bundles into plates every single day and then to be imaging on the night. And so it maybe take people 1 to 2 hours and a team of 4 to 5 people to be plugging plates, then you observe them, plug more plates, then you observe them. What we now have developed is with these robotic positioners, they actually vibrate the fiber bundles along the focal plane of the telescope. So it's a bit like taking your mobile phone and putting it into vibrate mode on a floor and getting it to vibrate to an exact spot on the middle of the floor. And so this is a very clever technique, and it's saving a lot of human power at our telescope now in a new instrument that we have called Hector. But this technology is not just useful for astronomy, it's useful for other areas as well. So for example, the fiber bundle technology that I just talked about is now being used by AT&T Bell Labs for communications in the US. And it's also being used along with miniature spectrographs that we developed for horticulture, by Horticulture Australia, for food safety sensors on farms. And so these little robots with solar panels all over them are going on farms, and they're using the spectroscopy to look for bacteria. So bacteria like salmonella, ones that give you really bad food poisoning. People have been getting bacteria from things like bags of spinach, bags of broccoli. And so they're now wandering along the farms and looking for the bacteria before it ends up in the supermarket and making people sick. The other thing we're doing is we're combining lasers with the fiber optics, and this is also helping for environmentally friendly weed control. So they can actually image and then identify which plants are weeds, and then they zap them with the laser and it burns the weeds, and so they get burnt up. So here's a laser one that's been zapped, and these other ones are the controls, and they're still alive. And so this is a really nifty technology that's actually come out of astronomy. So we're having an impact in agriculture and farming as well as communications. We're also doing nationwide engagement in STEM, and we're really proud of our nationwide STEM engagement programs. We have a range of programs. We've got a Telescopes in Schools program, which I'm going to talk about. We're developing an Astro in the Classroom program for primary school students to really help deliver the astronomy curriculum to students. We've got an Indigenous work experience program that it's been delayed due to COVID, but we're just about to start it this year. And then we're in the middle of producing a virtual reality production where students at high schools will be able to enter virtual reality and go to the Epoch of Reionization and do experiments using tools and scales and thermometers in the gas and on the atoms at the Epoch of Reionization using the headsets with moving the hands. It's a very exciting program. And so I'm just going to expand a little bit on our Telescopes in Schools program. We're really proud of this program. We started in 2018 to 2019. We take a telescope which is donated, and we take a telescope to each school, and astronomers come to the school and provide training both for the teachers as well as for the students on how to use the telescope. And then on our website, we offer materials and videos in what projects to do and how to use the telescopes. And we also provide YouTube videos and teacher research project ideas for those telescopes. We've got really high demand. Currently we've got 150 expressions of interest from the schools. It's way more than we can actually do, but we're obtaining more funding at the moment. And we've received an $85,000 federal government STEM engagement grant for this program, which is really helping us to deliver this across the country. In 2021, we started collaborating with the Chabal Indigenous Higher Education Centre at the ANU, and this is allowing us to introduce the Indigenous Night Sky in this program, and that's taught by the Gamilaroi Yualarai man, Pete Swanton, who's based at the Australian National University. So in 2018 to 2019, we reached 3,000 students and 3,000 community members. And then 2021 to 2022, we're targeting 7,000 students in 25 locations across Australia. And we're targeting rural students in particular because students in rural areas really don't have the access to the types of programs, the after-school programs and weekend and school holiday programs that kids in the cities already have access to. But in the rural schools, there's a beautiful night sky. They don't have a large amount of lights around, which would be impacting their ability to see the stars and the Milky Way. And so it's actually an ideal opportunity to get students excited by science. And so this is a plot here of where we've been targeting in our Telescopes in Schools program. And so we're going for schools that have low socioeconomic status as well as minority, regional and remote schools. And so we really are targeting all over Australia for this program. And we're planning on expanding it over the next few years. And finally, I just want to summarize with where we're going. What are we looking at in the future? So really, the next decade is critical for readiness for the next generation of telescopes. This is probably my favorite news headline. Whoa, new and giant telescopes ahead, which is absolutely spot on correct. There are new and giant telescopes ahead. And so we've got to be ready. We've got the James Webb Space Telescope just about to bring in data. We've got the Vera Rubin Observatory is going to start surveying the whole sky, enormous amounts of data, and that's going to go for around 10 years. The Nancy Grace Roman Space Telescope is going to be fabulous for looking at extrasolar planets and the atmospheres around those planets. We have the extremely large telescopes, both in Chile as well as in perhaps in Hawaii, and they're going to come online probably towards the end of this decade and early next decade. And then we've got the Square Kilometre Array coming towards the end of this decade as well. And so what we're really trying to do is to identify the major science programs. We need the teams working together across radio and optical and infrared and theory. We need to have leaders being trained as well as the models, and we need to know what we're going to look at. We need to know what are our exciting targets, and we need to have our data processing methods ready because these telescopes are going to bring in petabytes worth of data every single night, and we absolutely need to be ready for it. So it's a very exciting time to be in astronomy. Okay, and I just would like to say thank you for giving me the opportunity to share this with you today, and I would be happy to answer questions. I'll stop sharing my screen.
Thank you, Professor Lisa, for giving not only a compact overview of Astro 3D project, but also, talking about various initiatives that have been taken in Australia including gender equality, including public outreach and educations. It is really inspiring how you are trying to engage the school children and bringing them into astronomy, so they can they can take future challenges that's coming up with all these larger facilities in 2040 or 2030. I mean, so these are all inspiring. Thank you so much. Now I will invite my colleague Biresh Singh, Dr. Biresh Singh, to conduct the question answer session. Biresh, over to you.
Thank you very much, Manas. So we have this seminar or Vyakhyaan running over two platforms. One is WebEx and another one is YouTube. So first we would like to go to the audience of WebEx. So please raise your hands if you have any questions. Even you can write in the chat box and I can read.
So Biresh, can I ask one question first?
Yes, yes.
Okay. So Professor Lisa, you showed one of the simulation that is mappings. Okay. So where you were trying to see the distributions of various, molecules. I mean, for example, oxygens and things like that, how they are distributed. And what I see, the morphology looks like a little bit more like elongated and perhaps bipolar. And so, do you anticipate some sort of such things from your simulations?
Yeah, so we did in the paper that's just been published by Jin et al. In AppJ. We did simulate bipolar emission as one of the scenarios. So we've got three scenarios. One is bipolar emission, where you've got dense gas around the star forming region and it's escaped in some regions, and then it's ionizing the surrounding gas. We have another scenario where it's more uniform, and we've got another one where the gas is very clumpy, and they actually have quite large differences in where you see the different emission from the different chemical elements, so nitrogen or oxygen. And so it's actually quite interesting. Right now we're comparing the models with some nearby H2 regions. And yeah, absolutely. In the nearby H2 regions, we see quite a lot of bipolar emission. And so those models are going to be very useful, I think, in interpreting that data. And we're just testing the models at the moment.
Okay. So Biresh, can I proceed for another one?
Yes, yes, please go ahead.
Yeah. So I just want to ask whether Australia is part of both GMT and ELT. Is it,
it's part of the GMT. So the Australian National University, as well as an organisation that does it on behalf of all of Australia, they're both partners of the GMT. The ELT with ESO, we're only what we call a strategic partner. We're just a partner of the VLT, not the ELT yet. We'd like to become a full partner of ESO. We're not a full partner yet, so our government would need to make a full partnership with ESO in order for us to have access to the ELT.
And what about LSST? I mean, you are a partner of LSST?
Oh yeah, so LSST, we have a grant that's just been awarded where some astronomers have been awarded funding to be able to become investigators in the LSST. And so there's a number of astronomers who are now going to be, and their students and postdocs who are going to be part of the LSST. And so organizations or countries have to pay for investigators to be part of those programs.
Okay, thank you.
Okay, I do not see any hands raised. In fact, I myself had a couple of questions because I do not see any raised hands. So let me ask one question. This is about gravitational lensing. So you showed that with the gravitational lensing, we can probe high redshift universe. So is there any limit on the redshift? Or let's say with the JWST, how far we can see the galaxies in terms of redshift?
Yeah, it's a good question. So far, I think the highest we can go back is it's about 12 billion years where we can actually get a spectrum of the lensed galaxies, but it may well be that we can go back further. The trick is finding big galaxy clusters. And so the biggest galaxy clusters are nearby, and the light would either need to be bent around those, or we need to find much more distant clusters to be bending the light from more distant galaxies. And there are some clusters at around redshift of 0.5, 1.5 that we can probably use to lens more distant galaxies. And there is a James Webb Space Telescope early release science project that I'm involved in, which is aiming to detect high redshift lenses using JWST. But I'm not sure quite how high in redshift we'd be able to go with that.
Okay, thank you very much. Sashi, can you please ask a question? Unmute yourself.
Thank you, Professor Kewley, for that very nice and interesting talk. My question is regarding the issue of light pollution. So since you are involved in a lot of outreach activity and such, so how is it that you are working on the light pollution aspect? Is that an important issue for you in Australia? Or
yeah, it is. It is certainly around the cities. It is important, and also around Coonabarabran, where our main telescopes are in Australia. We had to get the Coonabarabran, the Siding Springs mountain site. We had to get the whole town to be registered. In Australia, a town can be registered as a dark skies site, and then there's requirements. Once a town is registered as a dark skies site, the government requires them to have, there's limits on lighting, and they have to have special street lights that just go down, and they have to be certain wavelengths. And so we did work on getting Coonabarabran to be a dark skies night. And there's also other astronomers in some of the other states which are out in the rural areas who are working on getting their areas to be listed as a dark skies night as well. It requires a lot of testing of the illumination that's around in the night sky, and then you have to submit an application to the government, and it takes some time for them to get approved. But yeah, that is very important. It's actually one of the reasons why we no longer observe on our mountain here. So I'm on a little mountain, it's a hill. It's not really a mountain, but it's called Mount Stromlo Observatory. And, you know, we used to do great surveys on this mountain, including, you know, looking for dark matter, and, you know, we did the Monte project on this site. But the suburbs are now right up against the mountain right there. And so the sky is not anywhere like what it used to be. And so we're right next to a city. And the city's doubled in size over the last 15 years. And so we actually don't observe here anymore. We just observe out on in the dark skies site.
okay, thanks. So I have a few questions regarding the Gala survey as well, but I think I will write to you separately. Thanks.
Yeah, Professor Banerjee seems to have a question.
Yes, Professor Lisa, I have a couple of questions. The first question is regarding the pandemic. How has the pandemic affected research institutions in general across Australia, in light of the fact that some effect on the Australian economy must have happened? So has the level of grants suffered any reduction in the last couple of years from the Australian Research Council to centers of excellence? And the second question is regarding possibility of Indian students who have just finished their bachelor's degree. What are the avenues for Indian students to join Australian research centers or universities? How do they apply to these research centers or universities? after they have a bachelor's degree in physics or astronomy? Thank
Right.
you.
Yes, so COVID impacted us in a number of different ways. It caused telescope closures, not radio astronomy so much, but the optical telescopes, and so it delayed quite a few projects. It also, because Australia locked down the borders, our students and postdocs were unable to reach jobs overseas. They weren't allowed out, and then we were unable to hire in because of the closed borders, and so we had many people delayed or not able to come to jobs. So it actually impacted the centre's ability to recruit and also our students and postdocs. So we had to we also weren't traveling at all, so we had a lot of travel money accumulating, so we took all that travel money we weren't using and we rolled it into a COVID extensions program where we provided it to students and postdocs who needed extensions for their projects, either due to delays because of telescope time, being delayed, or because they were unable to get to a job overseas. And so we were able to extend them. That's one thing we did. The financial impact has been huge on the universities because of the closed borders and the lack of international students. A lot of the universities actually depend a lot on the international students and international student fees. And so most universities in Australia had funding cuts. And so that affected academics on fixed term as well as on permanent positions. Some people lost jobs. And here at ANU, we had a 30% cut, which is really significant for a small department. And fortunately, however, the Australian Research Council wasn't impacted, and the Centre of Excellence funding was already existing before the pandemic came. And so we were in effect kind of sheltered from the major impact on the universities because we had the Centre of Excellence. And I think that's actually one of the good things about having a Centre of Excellence is it allows you to do a long-term program which is unaffected by the fluctuations you can get in funding due to recessions and all sorts of, pandemics and all sorts of things. So that was fortunate for us. And for all of the younger, astronomers in the centre as well for their careers. Your second question about how Indian students can come to Australia, yes, please come. We have a lot of Indian students actually in the Centre of Excellence and also Indian postdocs. So, for example, my student Anshu Gupta was a student, came from India, and she did research using the gravitational lensing technique and looked at galaxy clusters, and she's now a postdoc at Curtin University. She's now an Astro 3D fellow. Sonia Sharma was a student I also had from India, and she's now working at NASA Goddard Space Flight Center on gravitational lensing. And Ayan Acharya is now working at Johns Hopkins University, and he was a PhD student here at ANU, also in Astro 3D, and he was working on high redshift galaxies and chemical abundances. So we absolutely accept Indian students, and they do really well. And you just look at the university's websites, and there's specific deadlines. The deadlines are usually around September for international scholarships, and you usually find out in the January-February timeframe.
Thank you.
Okay, I do not see any hands raised in WebEx. From YouTube, we have a couple of questions. Prachi Prajapati, she wants to know that, when you spoke about gender equality and so the statistics comparing Australia and US numbers. So she said that what kind of scenarios exist between statistics of Australia and international students? I mean, when you're talking about gender equality, so is there any comparison between Australia and international?
So Australia is at around 35% women students at the moment, and In the US, I think it's actually is higher. I think the fraction of women students at many organisations is now 40 to 50%. Australia's a little bit low, however, there are countries in Europe where it's still around 30% and sometimes even lower. So it really depends from country to country, and it also is quite institution dependent as well. So some institutions will be at or close to 50-50, and others will be much lower than that. Can fluctuate with time as well. But there's quite a lot of data out there that's being published.
Okay. There's a second question. She wants to know that whether Astro 3D is aiming to attract more international students in upcoming projects and collaborations.
Yeah, so we're always looking for international students, and the Australian government has a program called it's called the International Postgraduate Student Scholarships, and student can apply for these scholarships, international scholarships, and you can apply to take them at any university in Australia. And there's a certain number each year that the government provides, and then the universities sometimes provide also their own scholarships. And Astro 3D also, our universities have money for specific Astro 3D student scholarships as well. So there's three opportunities, you could say, for student scholarships, and the number of students in our centre has been increasing over time. So we're still accepting students for all of these programs.
Thank you. I do not see any questions from YouTube further. So let me take this opportunity to thank you very much for patiently and elaborately answering all the questions. And now I would like to call upon my colleague, Dr. Vineet, and I think he will say formal thank you to you. Thank you very much. Vineet,
Thank you.
over to you.
Yes, thank you very much, Viresh. So that brings us to the conclusion of the 37th episode of PRL ka Amrut Vyakhyaan. I would like to take this opportunity to first thank Professor Lisa Kewley for accepting our invitation and giving an excellent talk on ARC Center of Excellence for All Sky Astrophysics in 3 dimensions, or in short, Astro 3D in PRL ka Amrut Vyakhyaan. Also, we are thankful to Professor Kewley for answering the audience's questions after the talk. Second, I would like to take this opportunity to thank our audiences on both the YouTube and WebEx platforms. Next, I express my sincere thanks to PRL Director, Professor Anil Bhardwaj, Dean PRL, Professor D. Pallamraju, and Chair of PRL ka Amrut Vyakhyaan Committee, Professor Nandita Srivastava, for all their support to organize this Vyakhyaan and successfully. I also thank my colleagues in Vyakhyaan Organizing Committee for successfully organizing and conducting this episode, that is the 37th episode of PRL ka Amrut Vyakhyaan series. I sincerely thank you all for being part of Azadi Ka Amrit Mahotsav and PRL at 75 celebrations. Kindly visit our website and other media platforms to know more about the upcoming events being held at PRL, in particular PRL ka Amrut Vyakhyaan. With these words, I propose the closure of today's episode of PRL ka Amrut Vyakhyaan. Thank you very much.
Thank you.